Hello, class. Gonna wait for a couple more people, then I'll get started. I believe that I forgot to say this for the last lesson, but there was no assignment corresponding to that. It was kind of a qualitative lesson. What's up, Spicy Pepper? I have had the same. I cut my own hair, and I've had the same hair clippers since 2003 approximately, and they broke last week, so I had to order new hair clippers. It's a tragedy. End of an era. I just got a text message that said, "Guess what?" And then now the person is not responding. It's like, I gotta know what. I'm not your home slice Astro Sloth 1. Don't talk to me like that. How dare you? Okay, so we're going to finish talking about electric fields by integration today. All right? So let's go ahead and get started. We're going to do two examples. The first example, okay, fine, if you make that emoji, I'll be your home slice. Fine. So we're going to do two examples. The first example is an infinite line of charge with constant linear charge density, lambda, which is, of course, dq dx. Okay? So we have this infinite line of charge. Okay, so it goes all the way to minus infinity. This way it goes to plus infinity. And now I'm going to get to learn what's up. Oh. Okay, that wasn't that exciting. And then there's a point P right here. Okay. And we might as well put this point P directly above the origin. Okay. Why would we put it directly above the origin? It's not going to matter where we put it because it's an infinite line of charge. right? So you're kind of like always in the middle of an infinite line of charge because it goes on to infinity in both ways. So I will put it directly above x equals 0. And its distance above x equals 0 is y. Okay. Now, if we think about it, which way does the electric field due to an infinite line of charge point? Okay. Which way does it point? And it turns out that it has to point, the electric field at point P has to point in the positive y direction. Okay. And there's the reason why is because of symmetry. Okay. So let's try to understand that. Suppose if we have an infinite line of charge and we flip it like that, we flip it, we go, it looks exactly the same, right? It's still an infinite line of charge. So let's suppose that the electric field had, maybe this direction. If we flipped that like so, then that would flip this electric field to point in that direction. You get what I'm saying? But the charge distribution is exactly the same as it was after it was flipped. Okay? So if you have an infinite line of charge, the electric field has to point directly away from the line of charge. So let me just draw that. I'll draw it down here at the bottom of the page, just so that we can see that. So if this is your infinite line of charge, then your electric field lines point directly away from the line of charge. And if you're below the infinite line of charge, they point directly down. Okay? So this is a side view. If we wanted to do a front view so that the line of charge is pointed directly at you, the electric field lines are going to point like so. So that's what the electric field lines look like for this infinite line of charge. Okay, so to calculate the electric field at point P, again, what we're going to do is we are going to look at an itty-bitty piece of charge. So this is a little bit of charge, dq, that is at location x. All right? So that means that this distance right here is x. So how far away is this itty-bitty piece of charge from the point P? That distance right here, according to the Pythagorean Theorem, would be square root of x squared plus y squared. Okay? This little itty-bitty piece of charge is going to create a little itty-bitty electric field, which I will call dE. All right. This angle right here is theta, and then this angle right here is theta. And so this is the there's a question in the chat. Is the line of charge assumed positive? Yes. In this case, yes. If you had a negative line of charge, then the electric field is going to point inward, okay, as opposed to out in a way. Good observation. And so this is the y component of that little itty-bitty electric field. So if we want to figure out what is dE, then dE is going to be k dq over r squared. All right, and so dq is going to be lambda dx by multiplying both sides by dx. So I have k lambda dx. And then r is the distance from this little itty-bitty piece of charge to the point P, which is square root of x squared plus y squared, which we then square, okay, to get x squared plus y squared. The y component of the itty-bitty electric field is going to be dE times cosine of theta, right? Because here's the angle and it's adjacent to the angle. And because these are vertical angles, someone told me the term last time I was here in class. These are vertical angles, and so this angle is the same as that angle. And so I can see that cosine of theta is going to be y adjacent over hypotenuse. So cosine of theta is going to be y over square root of x squared plus y squared. All right. So that means that the so that means that dE, the y component of it, is going to be k lambda y dx over x squared plus y squared to the 3/2. Okay, so where did I get that from? Notice how the 1 over r squared is this, and then the cosine brings in this denominator. And so when you multiply this by that, you get a 3/2 power. Okay, and then we also have this factor of y from the cosine of theta. All right, so how are we going to compute the electric field at point P? Well, using symmetry, we already deduced that the electric field is going to point upward. Okay, so I know that the electric field is going to point in the j direction, and this comes from symmetry. Okay, and so since it points in the j direction, it doesn't make sense to do anything with the x component. We're only going to do the y component. So we're just going to add up the y components of the electric fields. Okay. All right, so we don't even need the x component. So even though this little itty-bitty piece of charge creates an itty-bitty electric field that has an x component, when we add all of those x components up, the total result is going to be 0. Okay, so we're not even going to worry about we're only going to worry about the y component. So now I plug in here, so I have j hat times the integral of k lambda y dx over x squared plus y squared to the 3/2. All right. Now what our integration variable is x, where x is the coordinate along the infinite line of charge. And we can see that the infinite line of charge extends from minus infinity to plus infinity. So our limits of integration are going to be minus infinity to plus infinity. All right. And because our integration variable is x, all right, because our integration variable is x, I can factor out this stuff because none of that depends on position. Now, if this infinite line of charge had a charge density that depended on position, we wouldn't be able to factor out the lambda, but I'm saying that it's constant. So I factor all of that stuff out, and I get k lambda y times the integral from minus infinity to infinity of dx over x squared plus y squared to the 3/2. I dropped out there for a second, so I'm just going to wait. I'll explain that again. K, lambda, and y are constants, so I factor them out. And so you just have this. So this is the integral we want to solve. Now, this is the point where we leave physics and we go to math. All right. Now, this integral is trickier than the one for the x component of the electric field. If you go to the last lesson, we calculated the x component of the electric field due to a segment of a line of charge. Okay? But this is the y component, and the integral is a little bit trickier. So we have to use a technique called trigonometric substitution. And so, again, you are perfectly fine plugging this into Wolfram Alpha and getting the answer to that integral. But I'm going to show how to do it just for completeness because I like doing integrals. Whee! They're fun. So for trig substitution, I'm going to say x equals y tangent of theta. Okay. So what does that do? So let's think about what that does. So first of all, I'll figure out what is dx. So the derivative of tangent is secant squared. So I have dx equals y times secant squared of theta d theta. All right. And then so that tells me what dx is going to be. Then I have to figure out what is x squared plus y squared to the 3/2. Well, x squared plus y squared is going to be y squared tangent squared of theta plus y squared. All right. And then I factor out a y squared, and I get tangent squared of theta plus 1. And this is just a rearrangement of sine squared plus cosine squared equals 1. So this is actually equal to secant squared of theta. And then I have to raise this to the 3/2. So that means x squared plus y squared to the 3/2 is going to be y squared secant squared of theta to the 3/2. Now take the 1/2 is going to remove the square, and then we just cube it. And so I get y cubed secant cubed of theta. Okay, so that's what that becomes after the trig substitution. And then lastly, I have to figure out what are my limits of integration. Okay, so if x goes from x is in the range of minus infinity to infinity, then what does theta go from? Well, if we think about the graph of tangent of theta, you know how the graph of tangent of theta, so here we have x and here we have theta. The graph of tangent of theta kind of looks like this. So here we go to plus infinity, and here we go to minus infinity. All right, and the value of theta where we reach plus infinity is pi over 2. Okay. And then the value where we reach minus infinity is negative pi over 2. Okay. So remember, when you do any kind of substitution, your limits of integration are going to change. And so when we switch to theta instead of x, our limits of integration go from minus infinity to infinity. They transform into minus pi over 2 to plus pi over 2. Okay? So we can take this and do our substitution. K lambda y times j hat times the integral. Now the limits of integration changed. All right. So now the limits of integration are minus pi over 2 to plus pi over 2. dx changed into y secant squared of theta, d theta. And then the denominator changed into y cubed secant cubed of theta. All right. So one of the things we can see is that I have 2 factors of y on the numerator and 3 factors of y on the denominator. So those are going to cancel out and make 1 factor of y in the denominator. So we get k lambda over y times j hat times the integral from minus pi over 2 to pi over 2. Okay. And then we have a secant squared on the numerator and a secant cubed on the denominator. Those will cancel out to leave a secant on the denominator. Now, as you know, secant is 1 over cosine. So 1 over secant is cosine. So that's our integral. And a handy-dandy fact to know is that if you have a trig function like this, here's cosine. The area, so this integral could be interpreted as the area of this bump. And the area of that bump is 2. All right. You could do this also by just integration, but I always just remember like, hey, that's 1 bump that has an area of 2. Okay. So the value of this integral is going to be 2. So that means that the electric field at point P is equal to 2k lambda over y times j hat. All right. So again, I want to reiterate that if you have an infinite line, the x components of the electric fields cancel out, and you are left with only a y component. Okay. If you have a finite segment of line, you are going to have both an x component and a y component in general. Okay. So that is an important point. All right, so that was the first example for today. And for your quiz today, you are going to have not an infinite line, but a finite line that goes from minus a to plus a. And so you'll be calculating the electric field. So all that would change is that your limits of integration won't be minus infinity to plus infinity. They'll be minus a to plus a. All right. So let's do a second example here. So this example is going to be a ring of charge. a uniform ring of charge with total charge Q and radius, let's call it A, radius A. All right, and so I'm going to draw this from a couple of different perspectives. So we have a 3D view. All right, so the 3D view is going to kind of look like, here's the ring. So the ring becomes an oval. Here's the center of the oval. And we go up a distance y, and there's our point P where we're going to calculate the electric field. Okay, and so this distance right here is going to be A. Now, because this is a 3D perspective, this is actually a right angle. Okay, we could imagine a side view or an edge-on view of this. So if you take a ring and you look at it edge-on, it just looks like a line. So it's just, all right. And here's the center of it right here. This distance right here would be the radius, A. And then we go up a distance, y. And here's a point P. Or we could think about sort of a top-down view where we just have the ring of charge, and then the point P is right there. Okay? So what we want to do is we want to calculate the electric field at that point P. So the electric field at point P what was I going to say? Where's my train of thought? So this point, oh, now I remember what I was going to say. This point P is on the axis of symmetry of this circle. So it's directly above the center of the circle, okay? Now, if we think about that, by symmetry, the electric field would have to point in the y direction, okay? Because if we take this ring of charge and we rotate it, that does absolutely nothing to the charge distribution, right? Because it's a uniform ring of charge, and so you're rotating it, and it's still a uniform ring of charge. Okay, so therefore the electric field, when we rotate it, it has to, if we rotate it, we can't have the electric field change. So that means it has to point along the axis of symmetry. Okay, I can't bend my finger because I was forging the other day, and I was hammering too much, and I got a big blister here, and now the skin is all dried out. Do you ever have that where it's like if you extend, if I were to point my finger perfectly straight, it would like tear the dry skin, and so I'm just kind of like leaving my hand limp. Okay, so we know that the electric field is going to point in the y direction. So just like last time, the electric field at point P is going to be in the j direction, and because we know that it's going to eventually point in the y direction once we do the integral, we might as well only add up the y components of the electric fields. Okay? So that's what we're going to do. So let's consider an itty-bitty piece of charge dq. And so I'm going to have an angle. So we kind of have two angles here that we have to be careful about. All right? There is this angle right here, which I will call theta. And so basically here is dE, and here is the y component of dE. All right, so this angle is theta. But then we also have an angle around the circle, like this angle right here. So I'm going to call that angle alpha. Okay, and so again, so kind of like here's dq, here is dq, and so dq is making an angle alpha. So here's alpha equals 0, and that's where it is. Okay. So first of all, let's figure out what is dq. Well, because it is a circle, I told you that whenever you have a circle, your integration variable x, it'll be some angle. And because the angle around this circle is alpha, we're going to have dq d alpha. So we have dq d alpha. And then we have a total amount of charge q, and we have a total amount of angle that is all the way around the circle, so that would be 2 pi radians. Okay? So what that means is that dq is equal to q over 2 pi times d alpha. So that's going to be important. We also have to figure out how far is dq from the point P. And again, that's the Pythagorean Theorem. So this distance from the center to dq is going to be the radius of the circle A. And then this distance is y, so this right here is square root of y squared plus a squared. Okay, so that means that r squared is going to be y squared plus a squared. Notice how one of the interesting things about this is that every piece of charge on this ring is the same distance from point P. All right, so this is actually independent of alpha. Because you want to think about this like a cone. If you have a cone, the edge of the cone, all the points on the edge of the cone are the same distance out to the tip of the cone. Okay? And then because it's the y component, we want to multiply dE by cosine of theta. All right? And so because these are vertical angles, cosine of theta is equal to y over hypotenuse, y over square root of y squared plus a squared. All right. So these are the bits of information we need. So in calculating the electric field, we're going to have J hat times dE, which is k dq over r squared times cosine of theta. So now we just plug in for all of these values. So I know that dq is going to be q over 2 pi d alpha. I know that r squared is going to be y squared plus a squared. And I know that cosine of theta is going to be y over square root of y squared plus a squared. All right. Now, if we look at our variable of integration, our variable of integration is alpha, the angle around the circle. So because we're including all of the charge in the circle, okay, we're going to go from 0 to 2 pi on this integral. Okay. Now here's the really nifty thing about this problem. All right. Nothing depends on alpha. So we can literally factor everything out. So I'm going to factor everything out because alpha is our integration variable. So anything that does not depend on alpha is effectively a constant, which can be factored out of the integral. So we get j hat times kq y over 2 pi y squared plus a squared to the 3/2. So that's all the stuff that got factored out. And then I just have the integral from 0 to 2 pi of d alpha. All right. This is a really easy integral. You could think about it as the integral of 1 times d alpha from 0 to 2 pi. And the value of that integral is just 2 pi. So that 2 pi is in the numerator, and it's going to cancel this 2 pi in the denominator. So all that's going to do is cancel out the 2 pi. And we get that the electric field at point P is kqy over y squared plus a squared to the 3/2 times j hat. Boom. All right, so guess what, kiddos? We have learned all of the integration ones that you can do with basic integrals, okay? So let me just summarize. You should try to master the following. So what are the examples that we have done? We have done a line of charge. Okay, so and then you're calculating the electric field up here. The line could be finite or infinite. And we had a point P that was like above the line, and we also had a point P that could be in front of the line if it's a finite line. If it's infinite, you obviously can't do that. You should be able to do a circular arc and calculating the electric field at the center of that circular arc. And then the third example that you should know how to do is a ring of charge, where we calculate the electric field at a point above the axis of the ring. And these are literally all of the examples you can do by integration. If you do anything more complicated than that, the integral becomes impossible to solve with normal means. Okay, you'd have to go beyond Calc BC to do that integral. Okay, so yeah, so the problems are tough, yes, but the number of possibilities for questions that you could get on exams and homework, etc., is very small. Okay, so if you can just focus on understanding the line of charge, the circular arc, and the ring of charge, you're golden. Okay, so that is my